So what is exactly rank nullity theorem statement? I just read first what exactly rank nullity theorem is. Let T from V to W be a linear transformation and V be a finite dimensional vector space, then dim of range space plus dim of null space equal to dim V. That is nothing but rank plus nullity equal to dimension of the vector space. How we should prove this statement? So very simple. First, what he has given statement, that we write as it is. After that, what we have to prove, that we will connect it to the given statement. Here, first line he has given, let T from V to W be a linear transformation and V be a finite dimensional vector space. That is why I am directly writing as it is as, let T from V to W be a linear transformation and V be a finite dimensional vector space. Okay. Using this, we have to prove that rank plus nullity equal to dimension of the vector space. So first we start from null space. This is very easy if you start from null space. Okay, first we will take it one number as dim of n of t. Let dim of, we have to prove that only we specified here, dim of r of t plus dim of n of t equal to dim v. Now we start from dim of n of t equal to m. Let dim of n of t equal to m. What is the meaning, definition of dimension of any subspace? Dimension is nothing but which has a finite basis which contains m elements. Okay, that's why we will take it here. N of t has a finite basis which contains m elements. According to the definition of dimension, we wrote it. Now, finite basis. Okay, I will take it one finite basis. Let s equal to alpha 1, alpha 2 and so on, alpha n be the finite basis of n of t. So then automatically in that m elements are there. Okay. So now it is a finite basis. What is the definition of basis? Basis is nothing but what? It is linearly independent and L of s equal to n of t. Definition of basis I have applied. Therefore, s is a linearly independent and L of s equal to n of t. That I specified as 1. In coming steps, I am going to use this statement again. That is why I specified as 1. Now, s is linearly independent and L of s equal to n of t. We got it. Now, also you observe it here. These are all elements of n of t only. Basis of n of t means what? They are elements of n of t, also subset of n of t. N of t means what? Null space. Null space means what? Definitely every element which is in S must be having image 0 dash. That's why I am going to write it as t of alpha 1 equal to 0 dash, t of alpha 2 equal to 0 dash, t of alpha 3 equal to 0 dash and t of alpha m equal to 0 dash, where 0 dash is the 0 element of W. Okay, fine. Now we will once again repeat this previously. Number 1 we have written, no, that is S is linearly independent. We will take it clearly. S is subset of V. Why? N of t is subset of V. That's why S is also subset of V. Because S is subset of N of t. N of t is subset of V. Automatically S is also subset of V. And S is linearly independent. So we roll back once again. Previously we learned it one basis extension theorem. In that we say that whenever S is linearly independent and S is subset of V, then S itself is a basis or S can be extended to form a basis. That statement we use it here. So by extension theorem, S is itself a basis or S can be extended to form a basis of V. Okay, S can be extended to form a basis of V, we have written here. So that's why we will consider another set here, that is S1. That is S1, we will take it here. S is itself basis or S can be extended to form a basis is there. That's why we are going to consider the new set S1 equal to extended set. I am going to consider it here. Alpha 1, alpha 2, alpha 3 and so on. Alpha m. Along with that, I am going to add it few more elements, beta 1, beta 2 and so on, beta n. So now this extended set is elements of V only. Now dimension of which is a basis of V I am taking here. Extended set which is also a basis of V. So now dimension of V, what it happens, how many elements are there in S1? m plus n. That's why dim v equal to m plus n. So we got it up to here m plus n. Now what we have to prove actually? We have to prove that dim of r of t equal to n. Why we should prove dim of r of t? You just see here dim of n of t we got it already. We assumed as m, and right hand side dim v is what? M plus n. Then automatically left hand side dim of r of t also must be equivalent to n. Then only it becomes as equal. That's why to prove the theorem it is enough if we prove that dim of r of t equal to n. Okay, now we do one thing. We consider one. We have to prove that r of t has a finite basis, because definition of dimension is what? R of t must has finite basis which contains n elements. That's why we have to prove that r of t has a finite basis which contains n elements. Okay, so r of t has a finite basis means first we have to consider one set in r of t. That is, consider the set s dash equal to t of beta 1, t of beta 2, t of and so on, beta 3 and so on, t of beta n, which is subset of r of t. This is actually considered subset of r of t. When you come to consider it as subset of r of t, now we have to show that it is basis. How will you show this as a basis? Now just look at here. Now we prove that s dash is basis of r of t. S dash is basis of r of t. How will you show it? Very simple. S dash is linearly independent we have to show, and thereafter L of S dash equal to R of t we have to show. So I have taken first line S dash is linearly independent. How we should show it? S dash is linearly independent. For every element of S dash we have to multiply one scalar. That scalar I have taken as C1, C2, C3 and so on. Cn belongs to F such that C1 into T of beta 1 plus C2 into T of beta 2 plus C3 into T of beta 3 plus and so on Cn into T of beta n equal to 0 dash. Now what we have to show? We have to show that C1 equal to 0, C2 equal to 0 and so on. How we should show it? Now we have with us only one statement, that is T is linear transformation. Now we apply this T is linear transformation. So this we can also write it as T of C1 beta 1 plus C2 beta 2 plus C3 beta 3 plus and so on Cn beta n equal to 0 dash. Now you imagine that this entire C1 beta 1 C2 beta 2 plus and so on Cn beta n as one alpha. T of alpha equal 0 dash means what? Definitely it is a element of n of t. That's why I wrote it as C1 beta 1 plus C2 beta 2 plus and so on Cn beta n belongs to n of t. Fine. Now this is belongs to n of t means in that n of t we have already one statement there in 1. That is, we said that S is linearly independent. S is linearly independent and L of S equal to n of t. So linear combination of elements of S is always definitely one of the element of n of t. Now this is also element of n of t. That's why we can write it as it's a linear combination of elements of S. So I have written as C1 beta 1 plus C2 beta 2 plus and so on Cn beta n equal to linear combination of elements of S. In that S we have alpha 1 alpha 2 and so on alpha m is there. That's why it's linear combination. I have written d1 alpha 1 plus d2 alpha 2 plus and so on dm alpha m. Now we will take it into the right hand side all terms. Then what you get? d1 alpha 1 plus d2 alpha 2 plus and so on dm alpha m minus c1 beta 1 minus c2 beta 2 minus c3 beta 3 and so on minus cn beta n equal to 0 bar. Thus d1 equal to 0, d2 equal to 0 and so on dm equal to 0, comma c1 equal to 0, c2 equal to 0 and so on cn equal to 0. Why we have written all are 0? Because we have already previously taken S1 is actually linearly independent. Why? S1 is basis of V, automatically S1 is linearly independent and L of S1 equal to V. So here linearly independent whenever it comes its scalars are 0. That's why I have taken as 0 for all scalars. All scalars. Next what we are going to get it. So just look at here. I have written the reason also, since S1 equal to linearly independent. Therefore C1 equal to 0, C2 equal to 0 and so on Cn equal to 0. We got it finally. Okay, now observe it here. So these results whenever we get it, then we conclude that S dash is linearly independent. Now we have to show one more, that is L of S dash equal to R of t. So how we are going to show it L of S dash equal to R of t? That we'll learn in the next slide. Look at here. L of S dash equal to R of t we have to show. So what we have to show, there are two sets there. Left hand side is also set, right hand side is also set. Two sets when they are equal, whenever one is contained in the another. So we have to show that L of S dash is subset of R of t. After that R of t is subset of L of S dash. Now look at here. Since S dash is subset of R of t, we have that because we have taken S dash is already subset of R of t. That is why automatically we are going to get it as L of S dash is subset of R of t. This is already we have proved in the beginning itself when we are going to learn it about the subsets in the starting definitions, basis and all those that we applied here. Now reverse we have to show, means R of t is also subset of S dash we have to show. That's why I wrote it this one as number 2. Next one, when we prove it R of t is subset of S dash, that is we write it as number 3. Now look at here. R of t is subset of S dash we have to show means what? One element in R of t we have to choose. That's why I'm choosing as beta belongs to R of t. That implies what happens. Now we come back with definition of R of t. R of t is what? This is nothing but range space. Range space means what? It is image elements. Image elements means what? Definitely it must has pre-image. That's why I'm taking as alpha belongs to V is the pre-image of beta. Therefore, we wrote it as there exists alpha belongs to V such that T of alpha equal to beta. Okay, now we come back with that again the same statement, beta equal to T of alpha, that equal to T of alpha whenever is there, just look at here, alpha plus I am writing as L1 alpha 1 plus L2 alpha 2 plus Lm alpha m plus and so on k1 beta 1 plus k2 beta 2 plus and so on kn beta n. Why I am writing like this? Alpha is what? Element of V. Element of V means what? We will go back with the S1. S1 in that I specified that alpha 1, alpha 2, alpha m extended set, that is beta 1, beta 2 and so on beta n. That's why we are going to write it the linear combination of elements of S1 because it is the basis of S1 is basis of V. That's why I am going to write it as alpha is also a linear combination of elements of S1. That's why I have taken both combinations here. Now I am going to apply it linear transformation here. Since T is LT, no, that's why I am writing as L1 into T of alpha 1 plus L2 into T of alpha 2 plus and so on Lm into T of alpha m plus K1 into T of beta 1 plus K2 into T of beta 2 plus and so on Kn into T of beta n. Now that is equivalent to what we write. Just see here, T of alpha 1 we already got it from 1. You roll back 1 and you see that alpha, T of alpha 1 is what? 0 dash. That's why in place of T of alpha 1 I wrote it as 0 dash. In place of T of alpha 2 I wrote it as 0 dash. And so on T of alpha m as 0 dash we have written. Because it is the null space elements. That's why images are 0 dash that we already discussed that I used here. So after that, remaining as it is we wrote it. Now we got it as k1 into T of beta 1 plus k2 into T of beta 2 plus and so on kn into T of beta n. You observe that this is a linear combination of elements of S dash, because S dash contains T of beta 1, T of beta 2 and so on T of beta n. So that's beside we have k1, k2 and so on kn are there. That's why it's a linear combination of elements of beta 1, beta 2 and so on beta n. That belongs to, we write it as L of S dash. So that is we got it. So beta belongs to R of t I have taken. Beta belongs to L of S dash, we got it. Therefore we can write it as R of t is subset of L of S dash. So from 2 and 3 I say that they are equal. So we write it as L of S dash equal to R of t. So once we got it this, we say that S dash is basis of R of t. Now if you take it this, S dash is basis of R of t, dimension of R of t becomes as what? N elements. I wrote it as therefore dimension of R of t equal to n. Now we come back and see in the statement left hand side dim of R of t plus dim of n of t. Dim of R of t I got it as what? N plus dim of n of t is what? M. That is same as m plus n. M plus n already we got it as dim v value. That is whether is equivalent to dim v, we wrote it. Therefore theorem is proved. Hence the theorem is proved, we conclude. This is the end of the theorem proof.